Alright, we're going to go ahead and continue our work here in section 4.2, dealing with complex solutions for equations. So as you guys saw in lecture 29, we're working with solving polynomial equations that occasionally are going to have complex numbers as their solutions and not strictly real solutions every time. So to keep things going here, we're going to go ahead and visit the last objective that we talked about in lecture 29, which is finding zeros for polynomial functions, and then we're also going to spend some time talking about how to find polynomial functions based upon their zeros. To start things off, let's go ahead and focus on the first half, finding these zeros for polynomial functions. This is going to revisit a lot of techniques from college algebra and also hopefully enhance them a little bit now that we have a slightly deeper understanding of our complex number system. Let's go ahead and get into some examples though. Let's go ahead and take a look at the following. We have here the function f of x equals 3x squared minus 4x plus 5. If we want to find the zeros, we talked about this in lecture 29, that means setting f of x equal to 0 and then solving for x. So this is the same as solving the equation 3x squared minus 4x plus 5 equals 0. Now, how would we tackle something like this? How would we go ahead and work on finding these solutions? Well, for something like this, I would look at it and say, okay, the highest power of x that we see is 2, so this makes it a quadratic, and it has 3 terms, so it's a quadratic trinomial. So my thought process here, my flowchart is saying, okay, quadratic, expect 2 solutions, possibly complex. It has a linear term, so we're not going to use the square root property. Since it's a quadratic trinomial, 3 terms, this means that what I'm probably going to try is to go ahead and see if I can factor this. Can I go ahead and split this into 2 linear factors that can then use the zero product property to find my solutions? Let's go ahead and pop over to the notepad and take a look-see. So again, for this particular polynomial, what we're working with is f of x equals 3x squared minus 4x, and then I believe it was plus 5. We're going to look at this and say, can we factor it? That's the first place that I go every time. A times c, 3 times 5 is 15. Middle term is negative 4. Well, 15 only has a handful of factors, 1 and 15, 3 and 5. And neither one of these is going to have a difference of 4. So this is not something that factors using our standard methods. It does still factor, as we learned in the last lecture. Any polynomial has that set of factors that it can be written as under our linear factorization theorem. But in this case, to find those factors, we're going to break out our quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We'll go ahead and try and simplify this. I'm going to focus on the discriminant first. In each case, the discriminant is always a good place to start, mostly because it tells you what type of solutions you should expect, but also because it allows you to take a pretty complicated formula and chunk it into smaller parts. So this is going to be 16 minus, looks like 60. So 16 minus 60, that's going to give us negative 44, I believe. So this will be negative 44 underneath the radical, all over 6 now. I also went ahead and simplified this up front and our denominator as well. 44 does have a perfect square factor. It has 2, in fact. It has 4, but it also has negative 1, which we've now learned is going to give us I. So this is going to simplify as 4 plus or minus 2, the square root of 4, I, the square root of negative 1, times 11, the remaining part inside of our radical, all over 6. We'll write this in standard form and also simplify at the same time to turn this into 2/3 plus or minus I times the square root of 11 over 3. And there we have it, our 2 complex conjugate solutions to that particular quadratic. So this is kind of the thought process that we would have put up in basic college algebra. Take a look at the polynomial that I'm given and think about what techniques apply. Highest power of x is 2, so it's quadratic. Linear term exists, so let's try factoring. Factoring didn't work, so let's brute force it and use the quadratic formula. there's a basic flow chart to the thought process that we want to apply to the vast majority of these problems. It gets more complicated with higher degree polynomials, but there's always this thought flow as we go through each piece. Alright, back over to the slides themselves. Let's go ahead and take a look at another example included here. In this case, we have the following. We have f of x equals x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. We're told to find all of the zeros, but we're also told one of the zeros at the start. We're told that 1 plus 3i is a zero of this function. If we look at this function, it has all real coefficients, meaning our conjugate zeros theorem is going to apply. This 1 plus 3i as a solution implies the existence of another solution. 1 minus 3i must also be a zero for this polynomial. So in this case, we actually have already gotten two of our solutions for the price of one. Knowing this particular value is going to give us a big leg up on what to do from here. In this case, since I'm supposed to find all of the zeros and I'm given one out of the gate, I'm then also given a second because it was a complex zero, so its conjugate must also work. Let's talk a big picture for a second. This polynomial is degree 4, which means that I should be expecting 4 total zeros. 2 of them have been found, meaning there are 2 left to go. How can I actually find those 2 though? Well, this is going to be using a concept from our linear factorization theorem. Since we know 2 of our zeros, 1 plus 3i and 1 minus 3i, we know 2 factors, x minus 1 plus 3i and x minus 1 minus 3i are also factors of this polynomial. You've already kind of noticed that I've used the words zero and solution interchangeably. You could also loop the word factor in as well. Factors, zeros, roots, solutions, they're all playing off of the same concept. A value that makes this polynomial function equal 0. But why we want to use these is going to become relevant in the following slides. We're going to go ahead and take a look at these 2 factors and multiply them together. So we're going to take x minus 1 plus 3i, x minus 1 minus 3i, and find their product. Since they're conjugates, this is actually going to be something that's fairly straightforward. Notice here that they've rewritten them to help us a little bit. This is x minus 1 minus 3i, x minus 1 plus 3i, meaning that we can make use of our conjugate product property that we've already seen. We're going to square the first term and square the second term and take their difference. So this turns into x minus 1 squared minus 9i squared, which then simplifies to x squared minus 2x plus 10. Okay, but what's the point, Mr. Johnson? Why are we doing this? This seems like we're getting further and further away from finding all the zeros for this particular polynomial function. Well, the idea is this. In this case, these are 2 factors that are already known. We can remove them from the current polynomial. Since they are factors, we can essentially divide them out of the polynomial itself. We needed them to be multiplied together to get something that was easier to work with. If we were to try and divide our polynomial by something like x minus 1 plus 3i, we can do it, but it's a little bit messy. In this case, it's much easier to divide by x squared minus 2x plus 1, where we have all real coefficients. And it's actually shown here on the next slide. We're doing polynomial long division. So we're dividing x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60 by x squared minus 2x plus 10. A couple things to talk about here. It's probably been a while since you've done polynomial long division. A lot of people learn synthetic division, which is perfectly useful, except not in this case, because the polynomial that we're dividing by is not degree 1, it's degree 2. So long division is kind of our only way out here. If it's been a while since you've seen this, let me kind of talk you through it here. What we would be looking at is looking at a quotient of the leading term of our dividend and the leading term of our divisor. So x to the fourth divided by x squared gives us x squared. That's where the first part of our quotient came in. But what we then do with it is we remove x squared groupings that are x squared minus 2x plus 10 in size. So we actually take this first part of the quotient and multiply with each part of our divisor. That's where this line comes from. X to the fourth minus 2x cubed plus 10x squared. We took this divisor and multiplied by the part of our quotient. And then we subtract it. They're missing that sign here, but that's what's going on. x to the fourth minus x to the fourth is 0. That's by design. This should always disappear. Then we have negative 3x cubed minus a negative 2x cubed. So minus a negative, we're adding 2x cubed. That leaves us with a negative x cubed at the end. 6x squared minus 10x squared leaves us with negative 4x squared. These two just come from the subtraction. This 2x is being brought down from the next part. We then continue the polynomial long division process by looking at our new leading term here. For our dividend, negative x cubed, but again, we divide it by x squared. Negative x cubed divided by positive x squared gives us negative x, the next part of our quotient. And we repeat the process. Take this part of the quotient times our divisor, x squared minus 2x plus 10 to give us negative x cubed, plus 2x squared minus 10x, and just like before, we subtract it. This time gives us negative 6x squared plus 12x. We bring the negative 60 down and repeat. We end up with a final quotient of x squared minus x minus 6 with a remainder of 0. And obviously this should have a remainder of 0 because we already knew that x squared minus 2x plus 10 was a factor of our polynomial f of x. Okay, this seems like a weird detour to take. Why did we do this? Well, the idea is now that we've removed the two known solutions, we can work with the remaining factor to find the last two solutions. X squared minus x minus 6 contains our last two solutions for this particular polynomial. And thankfully, in this particular case, x squared minus x minus 6 actually factors into two real number factors. This is going to factor into x minus 3 times x plus 2. So this gives us our last two solutions, positive 3 and negative 2. So we needed a little bit of help getting a leg up on the polynomial. We needed to know, based upon one of our zeros, that its conjugate was also a 0. And then from there, we could go ahead and remove them as a factor. And from there, factor the remaining polynomial to find our last two solutions.